In order to have formulas for sequences and series, we have to talk about sequences and series that have particular types of patterns. And today's particular type of pattern we're going to be working with is a type where the way the sequence works is by repeatedly adding something over and over again. So this is a fairly simple type of sequence. And you can imagine that the next type we're going to be talking about will be repeatedly multiplying, and that's going to be geometric. We'll look at that in 14.3. So if we look at, say, this first example, 2 to 4, 4 to 6, then to 8, here the number that's being repeatedly added is 2. This other one here, the b's, it's a little less obvious what's being added, but here the thing that's being added is negative 3.5. And that's a pretty important example because it illustrates the idea that when we say adding, you could maybe say subtracting, because adding a negative, that's the same as subtracting. But it still falls under the same heading as an arithmetic sequence. So both adding and subtracting are legitimate here. The thing that you are repeatedly adding is what we call d. That stands for the difference between any two terms. And in general, if you're having trouble figuring out what d is, then actually work out the difference. It's like the name tells you exactly how to work it out. Like with this one here, if you weren't sure what you were adding each time, you could have done 1.5 minus 5 and figured out that it was negative 3.5. Now, for the individual terms of an arithmetic sequence, that part's relatively straightforward. You're going to have some random first number, and then the second number is going to be the first number plus something. So a2 is going to be a1 plus whatever your d happens to be. And then a3, you're going to add d again. So at this point you'll have 2 d's that you've added in. And then when you get to the fourth term, you'll add another d, and so on and so on. So what we want you to notice out of something like this is that there's clearly a pattern. It's a very simple pattern. If you're trying to figure out a later term down in the sequence, like the 20th term or the 50th term or something like that, the formula is that you start with a1, and then you add some number of d's. There's going to be a coefficient here in front of d. But the part that people tend to get a little wrong because they're not paying quite enough attention is what the coefficient is. And notice that with the fourth term, the coefficient wasn't 4. With the third term, the coefficient wasn't 3. The second term, the coefficient wasn't 2. So you don't just put an n here. It's not quite that simple. But it's close. It's almost that simple. When you were talking about the fourth term, you had a coefficient of 3. Third term had a coefficient of 2. Second term had a coefficient of 1. So if you just subtract 1 from whichever term you're on, then you can just use that as the coefficient. So as an example, if you were trying to figure out the 73rd term, it would be a1 plus 72d. The important part that people tend to get wrong is this part here. You don't put a 73 in front of the d, you put 1 less than whatever the subscript is. So, here's an example of the kind of question you're going to be expected to answer using this formula. This one tells you some information about the sequence, and then your job is to figure out what was the first term and what was the d, because if you know the first term and you know the d, then you can really know everything there is to know about the sequence. And the intention here is that when you're working a problem like this, you turn it into a system of equations. Like, for example, this piece of information here. The fifth term is 18. What that means is, when you use this formula to figure out a5, and you go a1 plus 4d, the answer you're supposed to get is 18. And that's an equation with 2 variables in it. a1 is a variable, d is a variable. And then if you take a look at the 9th term is 10, then that means when you plug in 9, and you get A1 plus 8D, the answer is supposed to be 10. And that's another equation that has the same two variables in it. So then you would move forward in this problem like you would with any other system of equations, like from Algebra 1. Two equations, two variables, that should be a pretty straightforward problem to finish up. Now this here, this page of information, this talks about the individual terms, the sequence for an arithmetic sequence. We also have to talk about a series where you add up the terms of an arithmetic sequence. And that's a little trickier. It's got a little bit more complicated formula, but it also has some interesting history behind it. It allows us to take a brief moment and talk about the history of mathematics. We talk about one of the greatest mathematicians in all of history, Carl Gauss. And Gauss, he was one of these really young geniuses where people knew he was going to be a big shot from a very early age. The picture I have here is from when he was already famous and later in his life. This problem here is something that he addressed when he was 8 years old. He was in some elementary school setting somewhere in Germany. I forget which town he grew up in. Can't remember right off the top of my head. But the teacher gave the class the task to add up the numbers from 1 to 100. And you or I know how we would approach a problem like this. We would go 1 plus 2 plus 3 plus 4. We would work the problem like this. We'd say, okay, and that's 6, and then add 4, and now we're up to 10, and add, 5, and now we're up to 15, and add 6, now we're up to 21. And somewhere along the way, we'd make a mistake, or lose count, or, we'd make a lot of little errors along the way, and it would take us a very long time. And honestly, maybe that's why the teacher gave the class this task. Maybe they just needed the class to quiet down and leave them alone for a little bit. But Gauss had the answer in seconds. He told the teacher, but I'm already done. The answer is 5,050. And the way Gauss got the answer is an important principle because we're going to use that same principle for doing our arithmetic sequences here in a second. So here's what Gauss did. Instead of jumping right into the problem and just brute forcing his way through the problem like you or I would do, what Gauss did was he took just a moment to think about the big picture. He thought to himself, okay, what am I being asked to do? I'm being asked to add up all of these numbers. And he asked himself, do I see any patterns in these numbers that I could exploit to get the answer quickly? And there is a pattern. If you look at it just right, the way Gauss looked at it, there is a super simple pattern. And the pattern is that if you work from the outside in, 2 numbers at a time, you get 101 for 1 plus 100. And then if you go the next pair in, 2 and 99, well, that's also 101. And if you go the next pair in, 3 and 98, that's also 101. And if you think about it, at one end of the pair, the number gets a little larger, and at the other end of the pair, the number gets a little smaller, and they always sort of compensate for each other. So on your way in here, you're going to get a bunch of 101s. So Gauss realized all he had to do to work out this problem was to do 101 times something. And then that part of the question is also pretty easy. We started with 100 numbers from beginning to end, and then we paired them up. So if we're pairing them up, that means we're going to have 50 pairs, half of however many there were. And even for an 8-year-old Gauss, multiplication was not really a challenge, and honestly, I don't think this particular multiplication would be a challenge for many 8-year-olds. It's got so many zeros and ones in it, it comes out 5,050 very quickly. So this is kind of a double lesson. One of the lessons is, this is the kind of thinking that geniuses have. It's not that their brains work necessarily faster. He certainly didn't just brute force it like this and just quickly or something. Genius is about noticing these cool patterns that once they point them out to the rest of us, we can look at that pattern and go, oh my gosh, that's so simple. It's the kind of hidden simplicities that geniuses notice. Now notice the reason that this worked was because at one end, as you moved along, the numbers increased by a certain amount each step. And at the exact same time, at the other end, as you're going backwards, the numbers are decreasing by the same compensating amount. That same pattern happens if you're doing any arithmetic series at all. D is how much it goes up at one end, but it's also how much it goes down at the other end. So here's how we actually build the formula. We think about this in general, where each individual term is built by adding D, like this, and so on. And for what we're doing here, it might help us a little bit to look at the end of the series and write down like a couple of terms right at the end. So, for example, that AN there at the end, previous to that, was AN minus D. Right? You're working your way backwards, and going forwards you add D, so going backwards you subtract D. And then, going backwards another one, we're going to subtract D again, like this. Oops, there we go. And the formula is a little easier to work out if we do it in a slightly different fashion than Gauss did, rather than pairing up numbers. What we're going to do is we're going to write the series down a second time in reverse order. So we're going to have AN here, we're going to have AN minus D here, we're going to have AN minus 2D here, so that we can kind of see how the pairs line up a little better. Writing it down twice makes it a lot easier to see that the pairs, the D's, will sort of compensate for each other. And then, if we add these two copies together, what we get is, well, Sn plus Sn is 2Sn. And then over here, you get A1 plus AN from the first pair. And then notice what happens in the second pair. You've got A1 plus AN, and the D's just sort of cancel out. So you get A1 plus AN again. Same thing happens here, A1 plus AN again, and so on through the whole thing. It's a bunch of A1 plus ANs repeatedly over and over again. How many? Well, how many terms did we have originally? We had n terms. So this would have been n times A1 plus AN, and then you divide by 2 on both sides, and that allows us to create the formula. The formula for adding up an arithmetic series is this. And I like to remember it in words, personally. I don't memorize this thing in symbols. I think of it as how many times first plus last, all divided by 2. That's the part that I have memorized. Of course, how you choose to memorize something is totally up to you. You can do it any way you want, but I kind of like the second one better. And then here's an example from my own life of using this formula. When my young children were, well, my children were young, they're much older now, they're 26 and 23, but when my kids were young, at one point I took them to see the musical Cats, because I think that's like a requirement. I think every parent has to take their kids to see Cats at some point. And frankly, I was bored, because Cats is a great musical for kids, but parents, not nearly so thrilling. So I was looking around the theater and I realized, these are a lot of people who paid for tickets for this thing. How much money did they probably spend to come see this production? And it was $45 for each ticket I had to buy, and I was looking around and I was thinking, I bet that's a lot of money. Now, if you think about it, the way the seats are set up in a theater, they aren't usually, in most big theaters, set up in a big rectangle. They usually have sort of a curved front row, and then it gets wider and wider and wider as you go back. And in the theater that I was in, the first row had 25 seats in it. I could count them. I just looked at all the little heads, 1, 2, 3, 4, 5. There are 25 seats in the front row. And then I counted the next row, and it was 27 seats. And then 29 after that. And basically it was one extra chair on the left and one extra chair on the right as you went backwards to make that wedge sort of a shape. And then there were 28 rows altogether. Here's a really important issue, and a lot of students get this part wrong. 28 is a different type of number than the 25, the 27, and the 29. The 25, 27, and 29 are counting how many seats are in each row, whereas the 28, the 28 represents how many rows there are. So those are not the same sort of thing. If you want to figure out the total number of seats in this, the 28 is the how many part of the formula, and then the 25, 27, and so on, those are the individual terms, so the first is 25. And then we run into a little bit of a problem, and this is a problem that happens almost every time when you're doing any kind of a sequence or series problem, either here in section 14.2 or next time in 14.3, and that is, we've got this little gap in the formula. We don't know how many are in the last row. Now, theoretically, if you're sitting there in the theater, you could just turn around and count the number of seats in the back row. But if you think about it, that feels really weird. If somebody in a theater is turning around and looking at the people in the back, that's just kind of a strange thing to do. So I did not try to do that while I was in the play. Instead, what you do is you go and you use the other formula from the previous page. And you use that formula to figure out how many seats are in that last row. The 28th row has how many seats? Well, let's see. First plus n minus 1 times d. D in this case, if you go from 25 to 27, 27, 29, d is 2. 2 times 27, that's 54. 54 plus 25 is 54, 64, 79. Feed that back into this formula here, and now you can figure out how many seats there are in the theater without turning around and being a weirdo staring at the people in the back of the rows. So in this case, once you're done multiplying that all out, it's 1,456 seats in the theater. Now, there's an extra little bit in this question because I also mentioned that each ticket cost $45. And if they have a sold-out performance, that means in one night they make over $60,000. No wonder they can afford all the makeup and stages, and they can spend months rehearsing and choreographing all the various dance moves and things. It's pretty impressive how much money you can make in a very popular musical. So note here what happened in this problem, how we were using one formula, but there was a missing piece of the formula, so then we had to go use the other formula as well. That is a common pattern. Get used to that. You're going to see that again in other situations.